Hello, everybody. It is the 20th of January. Thanks for joining us on Houdini Hangout. We're continuing through our journey through Vex using the cgwiki's Joy of Vex kind of course that Matt laid out. It's a 20-day course, and we are on day 17. We're going to go over day 17 and 18 today. We're just kind of cruising right along here. I got to be honest with you, this one is a bit of a doozy. There's a lot of information to cover here. There's a lot of spots where I could potentially get stuff wrong. And I'm just going to warn you that this one's going to be this one might be a lot. So we'll see how this goes, and we'll go from there. We've got a lot of information that we're going through today about Orient, which is a quaternion. And if you know anything about quaternion, it's that it's hard to know anything about a quaternion because they're really, really complicated four float vectors. And they store all of the information for rotation that you could really need in most cases. They're really complicated and can store a ton of information in four values. I held up 5 fingers there. That's 5. This is 4. So there's a lot to kind of unpack here, and I think it's going to be an interesting little journey tonight. It was really tough even just taking notes on this, so I might have to kind of keep getting my bearings throughout the evening here, so we'll see how this all goes. But I'm really glad to have you with us. It's been really exciting for me to go through this course and just be able to brush up on some of my skills, some of my knowledge, and hopefully for you, you're either learning something new or, maybe getting a little couple tips here and there to be able to become a better, Vex programmer in Houdini. So the normal stuff all applies. If you guys have any questions at all, which I really am guessing that there's going to be some questions tonight, because this stuff is, again, it's really kind of mind-boggling on some levels. So if there's anything at all that you are unclear of, please drop a comment in the chat. Just let me know what you're thinking, what you're getting hung up on, any confusions on anything here. If you're watching this, after the fact, please let me know if there's any, drop a comment and just let me know what's not clear, and we can hopefully, make those clarifications for you, for other people along the line. Because if you're having the question, the likelihood is that other people are going to have the question. And again, another thing too, I just want to make sure I'm always clear about is that I am certainly not the be-all end-all expert in Houdini. As probably anyone worth their salt would admit, there's way too much about Houdini to understand all of it. So while I'm trying to guide you through this, there might be some stuff that I even have trouble with or mess up or whatever. So if you're having trouble, don't feel bad or feel like, if you have a question, it's stupid. We've all been there before. And that certainly is something that's encouraged here, to have conversations and chat about what's going on here in Houdini. So tonight, like I said, we're going to be planning to go through 2 chapters, day 17, day 18. Day 18 should be quite a bit shorter, but day 17 will probably take, probably a good hour here to get through. So we'll see how this all goes and how it shakes out, and we'll go from there. So thank you again for joining us, and let's, dive into some Houdini here. All right, so here is our setup. It's kind of the same thing we've been using for a while here in Houdini, or in the Joy of Vex kind of course that we've been going through. We're mainly going to be using the grid today. I also have this box with a little wrangle underneath it because we're going to use that in a second as well. So here we are. Joy of Vex, day 17. Let me copy this and throw this into the chat for you. That will be where we're starting from here. Let me also turn on my turn on this here. Give me 1 second. That should be starting it up so you guys can see what I'm typing. I've also colored my background black today just because there's a couple times where that will actually be really helpful because some of the colors stand out a little bit better against the black background. So I was noticing that in Matt's walkthrough, so I think it should be true here as well. Actually, you know what? Real quick, I am actually going to change this because I'm thinking, so if you hit D in there, that's going to bring this up. I'm going to actually change this to gray and see how that works. See if that's a little bit better, if that's kind of a good medium, because I feel like it's a little dark. So anyways, all right, here we are. All right, let's jump into some Orient. So if you remember, if you've been following along in the last lesson, we were talking about using a normal vector and an up vector to kind of define a stable rotation, right? We can kind of skewer our object with an up or with an n, like from a normal vector from our input points. And then when we define the up vector, that can kind of determine how this rotation is going to be. So then we can easily kind of skewer our object with these two vectors and then move it around in a really stable way and be able to control it. So, so in this case, now we're going to jump into this scary kind of four float value quaternion, and this is definitely, there's some really in-depth stuff underneath the hood here, and I think the thing to kind of keep in mind while you're working through this is that there's a lot of stuff happening under the hood here involving imaginary numbers and things like that. And I think what you need to really do is just kind of take this on faith for a little bit here. We'll get into some more details as we go along, but we're going to try to just worry about the end result and not so much about every little detail that's going on with each of the numbers in the quaternion. We'll talk about them. We'll talk about kind of the base to the starting kind of level for a quaternion, but once you start tweaking them, they turn into numbers that aren't kind of human readable. They're not just you can glance at them and know what's happening. It's kind of abstracted away through some imaginary numbers and things like that. So that's the first thing to keep in mind. Now, I don't want to scare you away from that because there are some really nice functions that can help us deal with quaternions, and we'll get to those in a second. So another thing to keep in mind here is the link to the side effects site. I'm going to drop that in chat as well. This is the instance attributes page, and I'm going to open this up here and you can just kind of take a look at it. If we look, we can see the very top attribute is Orient, which is exactly what we're going to be talking about today. It actually this is the order in which they're kind of looked for. And if it finds Orient, that's the one it's going to go for first. It's not going to look at N or up or any of these other things here. It's going to look for this 4 float Orient. So that's kind of the top of the heap there. And so let's now start talking a little bit about what these Orient attributes are and how to kind of work with these quaternions. So we're going to set up this right here, and we're going to then start to play with some Orient attributes in there. All right, so here we go. I have this box. We were working on with one kind of last time, and I basically just have the unscaled version that we did from the last chapter. There it is right there. It's colored just so we can kind of have a nice visual representation of what's going on there. And we're going to add a transform here underneath a grid. We're also going to do a point wrangle. Oops. There we go. Point wrangle. And then we'll do a copy to points. And if I shift click both of these, oops, drop it in there, that'll copy it to both of them. And I'm just going to select all these, hit Shift L to just make sure I've got these all kind of organized. Maybe we can move this up a little bit here. So there's our general setup here. And so now we've got an attribute wrangle. We're going to throw this in there. So we're going to say at Orient is equal to, and we're going to set up our quaternion. This is just kind of the do nothing quaternion. Basically, it's it just keeps everything in its exact, kind of the standard orientation for an object with, Y up, X in this case facing to the right, and Z facing to the left, right? So this is going to be our orient. We're going to hit Control Enter, and there we go. Our boxes are now oriented exactly the same way as our kind of world axis is in this scene, right? So this is just kind of the base level kind of orientation, right? So we can write that out pretty easily. That's all well and good. But let's now look at how this can be kind of an interesting thing to do to set something like the orient, right? So now since we're going to transform this right here, and as we rotate this, look what happens. The boxes actually stay in their orientation, right? So we can move this in all sorts of different angles, rotate it in different ways, and this isn't going to change kind of their orientation. They're still locked in that orientation, which is a really neat thing to be able to kind of manipulate and take advantage of, right? Because otherwise, if we weren't setting that, right, if we just kind of turn this off here, those are going to move around and kind of try to orient on, based around that that normal attribute that's coming in, right? So now we can actually set these in a very specific orientation that we want them to be. But instead of, obviously just defining it based on this kind of base XYZ and their kind of home orientations, right? We want to actually be able to manipulate that, right? So let's set up some different variables to use, and then we're going to use the quaternion function to define kind of how to set up this orientation, right? So the first way to work with it is using this version of quaternion, the quaternion function that inputs an angle and an axis as its arguments, right? So you can see that right here. We have an angle and an axis for the arguments. So let's set up this this kind of wrangle here. Let's set the wrangle up this way. So we'll do a float angle. So we're going to declare that. We'll set that equal to a float channel called angle. And then let's also make a vector declaration and call this axis, right? And this is going to be a vector, and we'll call this also axis. So we're really doing some pretty straightforward naming here. And then we're going to set the orient equal to quaternion, and that's going to come up right there, right? You can see there's some other functions that might pop up as you do this. And we're just going to specify angle and axis, right? Just like that. And so now, well, nothing has happened, right? Because I'm just going to move this down here just to make sure we can kind of see what's happening. I'm going to bring in those channels that we just added there that we hadn't kind of initialized down in our parameter interface here. And now if we take these, we can set something like the axis to 1, right? And we can move the slider around, right? So we can maybe grab it at the 1 value, sure, like in the 1 level of our ladder, or in the just 1 decimal place, tenths, adding tenths or subtracting tenths. So there we go. We can kind of rotate it around now. So our axis is facing in the Y direction up. I'm also going to turn this transform back to where it was, right? So let's do that. All right. So we've got our, the axis of rotation is directly in the Y axis, and our angle, we can just kind of rotate it around like so. Great. So that's all pretty straightforward. However, we are building this orientation attribute, right? So let's take a look at what we've got going on there. I'm in my primitive attributes. So I'm going to go to my point attributes here. And let's just take a look at what's happening here as we do this. So you can see that this orient quaternion is kind of changing as we go through it, right? Maybe not giving any meaningful numbers to us. Like, it's kind of hard to tell why those are changing the way they are, but we're just kind of understanding that those are being calculated properly from these two values, right? Okay, so that's all well and good. Let's now add some more interest to this, right? Instead of just setting the angle based on, just a slider, let's set it to time. So we're going to do this. We're going to say at time, and everything else is going to stay the same. And now if we hit play down here, we're just going to have kind of this nice smoothly animating box spinning around on the Y axis. So Matt then kind of says that, well, we could actually collapse this all down to one line, right? We don't have to have it on 2 lines. What we could do is we could take this here, right? We could take time. We could copy this down to here for our angle. And we could take this and copy it down to here, right? And just do it on one line. And what I'm going to do here is actually just use the control / to comment those out, because we might come back to that in a second. But now we have this all written on one line here. So our angle is time and our axis is this axis. And that's going to do exactly the same thing. Nothing has changed. So we've just collapsed it all down to one line. And that's still pretty readable, still compact, but readable, right? And that's something that you can make kind of the decision for yourself as you're coding and going through kind of writing your own wrangles and things like that. So that's all well and good, but let's now maybe make this even a little bit more interesting and add in some more offsets. What we're going to do is offset it based on the point number. And in this case, I actually knew this was coming, so that's why I left some of these things here, because we're going to go back to using some of that code. So let's just go back here and actually we can just undo what I did there. Go back a little here until this is... There we go. Great. So, nope, I accidentally hit something. So that's all right. All right, so let's just declare a couple of these values or these variables up front. So we'll say float angle, like so, and vector axis, just like that. So that'll just help us clean this up a little bit. We don't have to write this quite the same. Cool. All right, so the axis is going to stay the same. We don't really need to mess with that at all, but we're going to tweak the angle a little bit to make it interesting. So we're going to start with the angle channel here. Then we're going to add in something. So let's do angle and we'll do plus equals. This is just going to add this to the angle. And so at ptnum, and we'll multiply this. So ptnum is the current point number we're iterating over. Remember, this is in our kind of our template geometry, or the second input. That's it. That this copy to point is taking these boxes and copying it over to, right? So we have a little error there because I didn't finish this line, but that's okay. We'll just do ch, and here, here we'll say offset, like so. And then we're going to do another line that says angle plus equals, and we're going to set that equal to, so we're going to add time multiplied by a speed. So this is kind of scaling the time that's coming in. ch, and here we'll say speed. Great. Okay, that's all working there, well and good. And let's add this in here, and we can start to tweak this a little bit here. So we can just say speed is equal to 1 maybe in this case. And we'll look down here to actually see what's happening. So there those are, and our offset is actually going to drive how different each of these will be as the point numbers kind of go along. So if we give it a little bit, it's going to only be slightly offset, right? And the more we give it, the more that they're really going to kind of diverge from each other. So if we just give it just a really tiny offset, it's going to kind of, you can kind of see this like sweeping across, whereas the higher it goes, the more it's going to be, you know, vastly different between each individual kind of row of what's going on here. The other thing too is we can change the axis. So we could set it to something like this, right? So now we've got the boxes kind of rotating on this global x-axis here. And, you know, that's matching up more or less with what Matt has here. We could do something maybe like 0.1, and that's going to only slightly kind of give a small offset between each kind of row that we're going down here. So, and then, you know, Matt kind of says, all right, let's play around with this a little bit, right? So let's change this to an axis of 1, and instead, let's put a 45. So 1 in that axis and 1 in this here. So we'll do it like that. And then maybe we'll give it a good, you know, maybe we'll even give it a little more speed, maybe do something like really small. So it's just kind of like that. And I don't know if you can totally tell here, but we're actually getting this really weird kind of behavior. We're getting this sort of like, it's not like a uniform speed that it's rotating in. It's kind of like, kind of goes like, and then it slows back down. It kind of has this ramp up and then back down. So in order to really see that better, let's set this to 002 to make it even more pronounced, right? 002. And now we can really see how pronounced this is going to be here, right? So we're not getting this stable, we're getting them like kind of like ramping up and down in speed, right? And so what's happening here is this, the magnitude kind of this vector, right? Because this is now a 2-unit long vector. And the magnitude of this vector is actually affecting the kind of that rotational, the way that this quaternion is rotating, right? The magnitude of that is actually affecting it. And so it's not having this smooth kind of constant rotation. It's got this kind of ramping up and down behavior that's going on. And so what we need to do is we need to normalize this. If you remember, we talked about normalizing our vectors in previous days of this course. And when you normalize something, you bring it back to being 1 unit long, right? So one, in this case, 1 meter, but one unit of length. And so this case, this would actually get set to 1, right? Like this. And so we're gonna have a nice smooth rotation around the z-axis in this case, and it's not going to be ramping up and down or doing anything crazy. So let's do that, and we can actually go back to this. We could even really accentuate it, something like this, right? So now we're getting this crazy fast rotation, and then it's slowing down. So if we go in, and instead of just having our axis here, like this, what we can do is we can add another line in here. Axis equals, and we'll say normalize, and we're going to add in axis here. So we're normalizing the axis and setting axis equal to it. So each time we're kind of taking that previous value. So here we've now set this axis value. We're taking this axis value, putting it into this normalize, and then setting axis equal to it. So now these should all just smoothly translate, no problems at all. In fact, if we go back to that same thing we were dealing with before, we'll have a nice smooth rotation there as well. So this is basically taking our axis that's, this kind of scaled vector and turning it back into this unit vector that is going to really smoothly transform this orient attribute. And you can see right here that this is, doing a whole lot, right? There's 3 of these components that are kind of constantly changing in our geometry spreadsheet here. I'll slow it down a little bit so you can see it a little better there. But there's a lot happening there, and it's not really human readable. We can't really figure out what's going on there because it's not something that's just an intuitive thing for a person to look at and understand. Maybe some people can, but I'd really be surprised. All right, cool. So let's now look a little bit further at this, right? So what we can actually do is we can actually, so this galloping kind of thing that we were talking about here, now we can kind of talk about just using the quaternion with an axis and using the scale of that kind of axis to define the rotation amount, right? So let's now kind of go through this code here and see how we might set this up, right? So we've got our vector axis still. We're not going to need this angle anymore. And in fact, we're going to get rid of all of this stuff here because we're not going to be using this right now. So let's get rid of that. And so now we're just working with the axis, right? So we're setting the axis. Then what we're going to do is we're going to normalize it just like we did before. And here we can say axis and then times equals, and then we're just going to set that to 0, right? So this is going to scale it to 0. So now, yes, exactly. It is angry at me because I need to change this as well. We're just going to put axis in there. So we're putting 1 value in here. So what you can actually do is, at least I should be able to, oops. Oh, no, okay, that didn't work. Sometimes in some of these fields, you can actually click and drag on like integers and things like that, but this isn't going to be one of those cases. Let me delete the spare parameters and just recreate them. We'll keep the axis in, I don't know, we'll do the 1, 1 kind of like that. And here we can do it at like 10, and we'll see that this now rotates them all. Because the magnitude, we're multiplying this axis times 10, so we're making the magnitude of that, 10 times larger. We've normalized it first and then multiplied it by 10, right? So we've now rotated that. So it's a little bit of a strange concept, but let's kind of keep going with this. And instead of doing it just by a number, let's set this equal to at time, right? This is going to be one of our pseudo attributes that's just kind of created by default, and it's going to go through each second, counting up 1, each time each second ticks away. So let's do that. And now if we hit play here, we should have some rotation that's happening here. I'm just going to turn off our the real-time playback just so we can see this a little bit quicker. And now we've got a nice smooth kind of rotation around that sort of weird 45-degree axis. And yeah, so everything's working. But let's talk about maybe better ways to think about this, because it is a little strange to scale a vector and have a rotation come from it. That's kind of a little odd. So Matt has this really fun example of what you might visualize that as. And kind of, he likes to visualize it this way with like a spinning top where you push it up and down and it kind of spins or whatever. And I think that's a pretty cool representation of it. It's not, a one-to-one example, but it's something to kind of think about, right? Where you're upping the scale of this thing, it's going to spin, around, right? So as you're pulling it up or down, it's going to rotate back and forth, right? And so it's kind of a really unique situation where, a vector can do kind of more than just maybe point something or change, a single direction, but it has like kind of multiple things built into it. So it's a really interesting kind of concept from that standpoint. So the next thing that we want to just talk about here is that there's something kind of odd going on. And hopefully you noticed it when instead of doing this time here, when I set it equal to, let's set this to the axis to 0, 1, 0. So we're rotating around the y-axis. And let's set this to 45. Oops, that's weird. Why didn't that set to 45? 45. Okay, so 45 degrees. Okay, that sort of looks... Is that right? That doesn't look maybe totally right. Let's set it to 90 and make sure that we're good. Okay, that's not 90 degrees. That is weird too. So what's actually going on here is that a lot of stuff that are taking in kind of angles, it wants those angles in radians, right? And so pi radians are equal to 180 degrees, right? So 180 degrees is the pi number of radians. So if you take half of pi, that's going to be 90, right? And pi 2 radians is 360. So hopefully that's something that can make sense here. Like Matt kind of describes this right here as 90 degrees. So we'll just type this in here. This is going to be a 90-degree rotation, right? So if I turn this on and off, we're going to get a 90-degree rotation. And also it's actually changing. Sorry. It's actually changing the axis too. But basically we're just rotating that box 90 degrees, right? So if I change it to 0, there, now it's rotated 90, and then back, rotated 90. Okay. So instead of doing all that craziness, we can use another function called radians, which is pretty straightforward. It converts from a angle, like a regular angle like we're used to radians. So what we can do is we can say radians like this, 90. So it's 90 degrees, convert it to radians, and that's going to be exactly the same as what we had before. So now we have a 90-degree rotation expressed in radians, and we're using that to drive our axis here, right? And so everything's working good. Yeah, so let's instead... let's go down and do this here too, because there's actually another way that you could do it. You could use this kind of built-in pi. So we'll do $pi divided by 2, right? This is all the same here. We've got vector axis, normalizing, all this stuff. And of course, this is going to be exactly the same. If we did pi just by itself, that's going to rotate it another 90 degrees or 180 from where we started. And Matt put in a little note for us here because he checked through this January 2023 as just before me as he was going through these things. And it's really interesting that they actually changed it. So you didn't even need to do this $sign anymore, apparently. So that's kind of cool. So that'll still evaluate to pi. And if we do pi divided by 2 like that, now we have the exact same thing as before, but we don't need a $sign anymore. So that's kind of an interesting thing. So you should know that pi is always going to evaluate to a value of pi to a certain number of decimal places. So just be mindful of that when you're writing your code. Don't name anything capital Pi. It kind of makes sense, but... All right. So anyways, what's the use of all this stuff? This is obviously, we're going through a lot of things here. What are we going to get? What's like the use of these rotations and all this crazy stuff? All right. So what we could do now is start to randomly rotate some stuff, maybe based on 90-degree value, you know, an amount of 90 degrees, like how many 90-degree rotations do you want to do around these boxes, right? So let's keep the first two things here. We'll keep the axis and the normalize here. But now let's change this around a little bit here. We're going to use the trunk function, which if you remember, there we go, trunk. If you remember, that's just going to cut off the decimals at the end of our number. So it's basically, it's sort of like rounding it, but it's not actually bringing it to the closest integer. It's just cutting the decimal off. Then we're going to do a random function inside of that, right? Random. And we're going to say at ptnum. That just means that as we go through each of those point numbers in our input geometry, give a different random number for each of those. It's going to be like our seed value is the point number. And let's multiply this times 4, right? And then, so now we've got a random number between 0 and 1 that we've multiplied by 4, which makes it between 0 and 4. And then let's multiply this by pi divided by 2. Right, so that is now, in fact, if you wanted to, you just to make it a little clearer for yourself, you could do it like that. So just to make sure that everything is kind of evaluating the way you want it to. And I think it looks maybe a little cleaner that way, maybe not. I don't know. That's just kind of up to you, but cool. So we've got pi divided by 2 like that. And so now we have these boxes kind of all randomly rotated like this. Okay, so we have a random rotation of these boxes based on, you know, whatever number comes back between 0 and 1, we're kind of now rotating it around in 90-degree increments. So there would be 4 90 degrees before you get, or 3 90 degrees before you get all the way back to, you know, 360 basically. So, so right now we have everything rotated to 0, 90, 180, or 270. So those 4 values. So that's all good, because we're, again, if you remember, truncating this means that you could get a random number that's 0.1 or whatever. You multiply that by 4, that's 0.4. You cut off the 0.4 and you have 0. So you're getting that just rotated to 0, right? So that's kind of what we're doing here in essence. Some of them will come back as 0. Some of those will be in the 1. Some of those will be 2 point something, and the rest will be 3 point something. So great. So instead of just doing it this way with just a random function, let's change it to noise. So we can change this random here to noise. It's just going to be a little bit more interesting, more structured kind of visual happening, right? And instead of doing point number, we'll do at p, and we'll add that time, at time to it as well. And the rest of it we can leave the way it is. We could just kind of maybe compact that a little bit more. We don't want it to kind of run off the end here too much. All right, cool. So sort of random, but it doesn't look as random as the previous one. So that's kind of a little weird. Let's hit play here, and okay, sure, that's working. Kind of interesting, right? Got an interesting value happening here. However, not as random looking. We're not seeing many of these red ones really, right? You're seeing only some of those. So let's kind of continue down and see what's happening here and why this is happening, right? So what we'll do is we're gonna look at what the what this noise kind of function is, or this noise is outputting, and then we can kind of evaluate why maybe we're not getting the randomness that we're hoping for. So what we're going to do is we're going to take up to here, keep this the same, but instead now we're going to take this noise function here. We're going to make an attribute just called A. One reason for that is it'll come right at the beginning of your geometry spreadsheet, so it'll be easier to find. And so we're going to take that, we're going to copy this noise function right here. We're going to cut this out, paste it there. All right, so we're going to just bring that up. And now we're going to say at A for that, right? So now this is going to make an attribute called A, and we're going to put it in here just in place of what we had before. The rest of it should stay exactly the same, and we'll just evaluate that. Now you can see we have a column called A here. And what we're going to do is let's now take a look at that and see what our noise is kind of between, right? What these attributes are between. So if you click on this top here, it's going to sort it. We can see, oh, This one's coming to 0.7. So that's not quite all the way to 1. And if we go the other direction, we're at 0.3. So that's kind of interesting, right? We're not quite going to the extents of that range anymore. So that's not good. We need to do something to kind of to fit that range better, right? And so kind of an obvious thing to change how something fits within a value range, we could use a fit. So we'll do that. So first we will take that. We'll go right below our A and we'll just say at A equals, and then we'll say fit at A, comma 0.4, comma 0.6, and then do 0 and 1. And if you don't remember how this works, basically what we're saying is we're going through here and saying, look at attribute A, the minimum value go to 0.4, the maximum value look up is 0.6, and set those two values. Now stretch that value out between 0 and 1, right? So these are our incoming numbers, right? So we're looking between 0.4 and 0.6 on our attribute A and stretching those values to 0 and 1, right? So we're kind of stretching it out to fill that whole value range. So now hit Control Enter, and sure enough, we have a much more random value now. We're seeing a lot more red. We can kind of slow this down a little bit and just kind of see what's happening here. And yeah, so we've got some more interesting look happening here, right? We've got a little bit more red that we're seeing, and things are kind of more random. So that's all well and good. But a really cool way to kind of work with this is use something like our ramp parameter that we've set before. So instead of doing this fit, let's do a ch ramp, because really a ramp is very similar, right? You can define where these two values are here by where your points are in the x axis, right? Where your 0 and 1 points start on the x-axis. So you could make a ramp and kind of pull those points in, and that'll set these values. And then you can, how high or low they go sets the second two values. So we can kind of use it in almost exactly the same way. So what we'll do here is, instead of doing this fit, we'll say ch ramp like that. And don't forget, when you're typing in here, if you do chr, you could do ch ramp like that, and kind of make sure you don't mistype either. So I don't always do that, but it's good to know that that's there. So then there's, Matt called this noise rearrange like that. And we'll say at A. So basically that's the name of this ramp, and we're going to use at A to drive the x-axis of this ramp. So we'll hit enter. It's going to go to 0 because we don't have a ramp. So let's kind of fill in that ramp from this kind of uninitialized channel reference here. Okay, so we've got our ramp. I'm actually going to make this a little bit bigger just so you can see it real well. And so what we can do here now is we can actually interactively kind of tweak this and change it. Something to keep in mind is that if you're playing back through it, depending on how you have your parameters set here, I think if you turn this off, that works better actually. But I think if this is on, it actually can do some really weird stuff. Yeah, I think that's the control that it doesn't like. Yeah. So there's reasons to have this on. I sometimes like to have this live parameter during playback, just it'll show how my parameters are animating and stuff. But the problem is that it causes some when you try to grab these things, it actually freaks it out. So anyways, now what we can do is we can pull this in on this side, and we can actually adjust the range of our values here. So I think really easy way to kind of visualize this, the values that we're setting, is by sorting this again. And so now we have our low values up at the top. So as I pull this in, you're going to see those values get closer and closer to 0, right? Great. So now that's like the kind of the top end of or the low end of our scale is set. The top end is still at 0.6 in this case. So let's now tweak that. So if we take this side and pull it, we can set that equal to 0.1. So now we kind of have this fit to our range, right? So if we play this back, we're going to get this really nice, kind of super even distribution of our noise. And something to keep in mind here too is when I hit stop here, you see this turned into a little dash. It might be a little hard to see on mine, but if you notice this turn into a dash, that just means this is no longer sorted. It's kind of a newer feature. And so as you play back through this, it says, nope, these aren't sorted. You can sort them again, right? So it doesn't like automatically try to sort them and just toss your point numbers all over the place. So it tries to keep it relatively stable for you, so they're not just, the point numbers aren't just jumping all over the place, but it is giving you a little visual there to say, hey, this isn't sorted anymore. So just something to keep in mind. The other thing that's really neat about this is you can actually kind of get some visual feedback here. So like you can push it this way and you're gonna get a lot more red in your noise. I'm just gonna turn this, no, we'll leave it on like that. Or you could pull it back and go this way, and you're gonna, you can change kind of the feel of this, right? How this is interacting here too. And like you could pull it this way, you can move these up and down. It's gonna change the values there. So there's a lot that you can do here to kind of get some really quick feedback using this ramp to kind of fit your noise, right? So, yeah. So okay. So the way that Matt is explaining this here in this next little section is it's kind of almost like we are tweaking the levels like in Photoshop or something like that. It's kind of like you're increasing or decreasing the contrast, right? As you bring them together, you're kind of increasing your contrast. As you pull them apart, you'd effectively be reducing your contrast. So it's kind of an interesting way to think about it. It's kind of like you're bringing up your darks and your lights and kind of shading your image that way. So like here we're getting, more darks or, more darks, less dark, you're kind of fitting it around and stuff like that, using your high and your low of a level, just like you would in Photoshop. So that's kind of an interesting way to think about it as well. So yeah, so we can see the data in our spreadsheet here too, but Mac makes a really great point that sometimes it's better to see that doing something else, right? So visualizing it in some other interesting way. So what we could do is add one more line in here and say at p.y is equal to at a. So this is going to set the value of our a attribute equal to p.y. So now these are going to go up and down based on how large a is, right? So we're putting that into, so we're seeing a go into our p.y here. So now as we play this, we can see these kind of jumping up and down like that. If we come back down here, we can see that we can make more of them kind of be part of this. We could sort of do it like this, where they're just kind of jumping up and down, just in a small little range like this. We could really extend the range like this, where it's like some of them are going up high and then staying. Most of them are sitting down low. And we could actually take this little, yeah, you can see just some of them will pop up there, right? Because those are the ones that have to get over this kind of threshold value in order to jump up. So then we can actually shift click both of these and slide them around, see different things here. So now most of them are going up and only a few of them are kind of staying down. So you can kind of slide this range around and get some interesting different results going on here. And you can make this really small, and these will kind of jump up and down, in different interesting kind of ways. So there we go. We've got some, different ways to visualize our data. You could do it through our geometry spreadsheet. You could do it right in the viewport and kind of see how things are working there. And this is really, pretty flexible, because we can turn that off just by coming up here and just hitting Control / and that'll comment it out, and hit Control Enter. And now we're back to where we were. We're not actually visualizing that anymore. And you could just say something in here, some sort of comment that would say like visualize data or something. You could just say it like viz data as p.y or something like that. And then if we do Control / there we go. So now that'll comment out the whole line, but the end comment will stay either way. So it's kind of an interesting little thing you could do there. So you comment out a line with a comment at the end of it, and it'll all stay commented. So anyways, let's now look at maybe a little bit of a different example here. I'm gonna hit stop, kind of reset everything here, because we're gonna start going back through, we're going to use a different example here. So let's come up here. We'll do Control middle click. That'll reset our expression. I'm going to come up here and delete all spare parameters. That's good. And we're going to just move some stuff around down here. So, all right. So we've, sorry, just kind of getting my bearings here. Let me just take a second to just kind of refigure out where we are here, because we're about halfway through this day. All right. So now what we're going to do is we're going to take the N and the up that we previously talked about. And instead of having those just define our, kind of these stable rotations for our objects, we're going to actually turn those into a quaternion, right? So we have to do this in kind of two different steps. We have to first turn them into a matrix, a 3x3 matrix, and then put that into our Orient, because there's no real way to go just from two vectors to a quaternion, at least not that I know of and not that Matt knows of. So we're going to do this in two steps, but it should get us where we want it to be. So let's throw this code in and just kind of take a look at what it's going to be doing here. So what we're going to do is we're going to set n equal to 0, 1, 0. So that's up in the y-axis. Then we're going to declare two attributes here, or two variables. Float s equals the sine of time, and float c equals the cosine of time. If you remember, doing those two kind of at the same time will give you the ability to make kind of circular rotations, right? Especially when you're talking about the components of vectors. That's kind of the way that the sine wave goes up and down, starts at 0, goes up, comes down to -1 and back up to 0. And then cosine is, shifted, and it starts at 1 and then goes back to 1. Those two working against each other will give you the proper vector that'll point kind of around in a circle, right? So what we're going to do is have those two equal our up vector. So our n is going to stay the same, and our up is going to kind of spin around. And we're going to use the set function like we did previously, and we're going to set s, 0, c, because we're using the sine of time, keeping this set to 0, and this will be the cosine of time. And we're going to go down here, do Orient is equal to quaternion. And then next we're going to have make transform. And this is going to take two vectors and turn it into a matrix. So we're going to say at n, at up. And we need one more parenthesis or one more bracket here. And I think that should work. And let's see what happens here. Sure enough, we've got rotating boxes. We've got the Orient here, which is a little bit crazy looking. It's kind of hard to tell exactly what that even means. It's kind of all these crazy numbers going all over the place. But if we look at up here and we just kind of slide through it, right, we can see that it's at 0, 0, 1. When we get to, they should kind of alternate, right? So we'll get to be up is equal to basically 1 here, and the x is equal to 1, and the z is equal to 0. It's close, at least. And they just kind of keep going around like that. Now, this is going to be in radians, I believe. It's going to be calculating the angle based on radians, so it's going to be a little different than it would be, but it would have to go to, I think, like whatever, 3.14 seconds before it does 180 degrees, right? So somewhere in here, right? That's 72 frames is 3 seconds, so it's right in here. We get to 180, right? Because that's the same thing we were talking about before with radians and all that kind of stuff. So anyways, here we are. We've got this. It's working. So let's just kind of Matt was just saying that, if we're ever in the unlikely scenario of having a matrix lying around, that's something else we can pass into the quaternion function. We're going to talk about matrices a little bit more in the next chapter, and maybe a little bit more in this chapter too. But let's just set a really basic matrix and go from there. So let's set this right here. And we're going to say... first, I'm going to take this and just say M. I'm going to get rid of all of this, and we're going to create, we're going to create a matrix 3. It's a 3x3 matrix. Call it M. And this is just going to be set to ident, and just the ident function, just by itself. We don't have to pass any arguments into it. What this is going to do is set up that kind of base, XYZ is all set to the world axis, right? No rotations, no translation, no anything like that. And this is going to give us just that standard rotation, right? So X is facing this axis, Z is facing this axis, and Y is facing this axis, right? So everything is kind of just in its default orientation. And this is called an identity matrix, right? That it's creating. And that's what the ident function does. So this is a matrix 3. If you wanted, so matrices come in two basic kind of flavors. The matrix 4, which is just called a standard matrix in Vex, that is a 4x4 array of numbers, and it gives you rotate, scale, transform, skew, perspective, kind of adjust. It's everything. It can do everything in one matrix. The 3x3 is a little bit less powerful, the matrix 3 that we just set up here. And the reason for that is it just does rotation and scale. So what we've set up here is a matrix 3, and we've basically just set an identity matrix, which, if you remember, we set the orient the same way here. This is basically setting this same exact orient right there. So it's giving those exact same values. So instead of doing the orientation based on setting a quaternion based on the orientation of vectors or a matrix or something like that, one thing that can be really helpful is to use the Euler rotations just, in each axis, X, Y, Z, and a certain number of degree rotation, right? Which is very normal. It's kind of how our parameters work for any of our transforms and things like that in Houdini. And so we can set up a vector parameter here in a channel that we can use. And we're going to do that now. And you can see how we'll be able to control this here. So what we're going to do is we're going to make this vector and call it rot, and we'll set this equal to the radians of this Euler rotation, right? So we'll say CHV. Oh, I spelled that wrong. I'm terrible at spelling. Something I'm really bad at. All right, there we go. So that's Euler. And then we need to use a different function here, because the quaternion is not just going to take in this vector and just be like, oh, obviously it's Euler's, vectors and stuff like that. Because if you just pass a vector into quaternion, if you remember, that's the one where as you scale it, it rotates. So what we need is this Euler to quaternion function. And this we can take in as the rotation vector that we made. And we're going to set the second argument to 0. We'll talk about that in 1 second. So there's that. All good. Nothing changes because obviously these are 0, 0, 0, and there's no rotation. So let's add in this Euler rotation here. And now we can take these and spin them. So this is going to spin it in the x-axis like this. This is going to spin it around the y-axis. And this will spin it around the z-axis. So you can see that we can now control this pretty well. And in fact, this is, I think, probably one of the most, if you were making parameter like this feels like probably one of the easier ways to do it rather than setting vectors based on direction. This could be a really easy way to kind of rotate something around. Maybe if you have, if you just want some parameters like this. So this is, I think, pretty easy to understand, at least from a human readable standpoint. You can just kind of look at this and go, oh, okay, it's rotating in these axes. So what is this second argument here? Why did we put this 0 here? Well, that is saying what order do we apply the rotations in? 0 puts it in XYZ right here. 1 looks like it would be YZX, and then 2 would be ZXY. So if you wanted it to be in some other order, you could do it that way. But we usually do XYZ just because that makes sense to humans, so we do that. Okay, so there you go. Euler to quaternion function, nice, helpful thing to keep in your back pocket. So we've come all this way, and what if we wanted to do something where you might have two orient quaternions that you want to blend between, right? Well, let's take a look at how we might do that. Let's first set up our two quaternions, right? So we'll do a vector 4. That's how we define quaternions. we'll say A, and we're just going to set this up as the kind of identity transform here, just the base transform. So that's just normal. We'll do vector for B. We'll set this equal to quaternion, so I don't have to type it. And then this is going to be the quaternion. Okay, so we're using up, and we're multiplying that by pi 2, so that's 90 degrees, right? So that's a 90-degree rotation, right? So we're using the vector 0, 1, 1, if I can type, 0, and we're multiplying that by pi 2. Now remember, we're in 19.5, so we can write pi that way. If you're in an older version, use the $sign because I can't tell you it's going to work for sure. But in 19.5, it'll do this, no problem. All right, and then lastly, we're going to do at Orient. We set that equal to slurp. And this is a fun little function that allow us to do a quaternion blend. And this will allow us to go between A and B, and we're going to blend it using a new channel that we're going to set up here called blend. And I need one more bracket there. And let's just delete our spare parameters here, and we'll add in our parameter here for blend. So now as we slide this, if you can think about what's going to happen, it's going to blend between A and B. So it should rotate 90 degrees. Sure enough, there we go. They're all rotating. Obviously not the most exciting thing in the world. So let's do something a little bit different here. So let's now give it a way to use some time in order to blend. So we'll declare a float variable called blend, and we're going to set this equal to at time modulo 1. And if you remember, time modulo 1 just means that as time comes up to 1, we're just going to be taking kind of the remainder of that, right? So it'll be kind of fluctuating back and forth from 0 to 1. So as time starts at 0, it'll be at 0 and go to 1, then snap down to 0 again and come up. So it'll do every 1 second, it'll kind of snap its rotation around. And you'll see that with the colors. It's actually going to look pretty smooth, but it's going to actually be snapping. Great. So I think that's all we needed to do in order to get that to work. Let's hit Control Enter, and let's hit play and see what happens here. No, I missed one thing. And the one thing I missed was changing this here to blend. So we need to just change that to the float variable blend. Now we should be good. And there we go. Boop, boop, boop. So it's rotating and then snapping back. Snapping, just like that. So, okay, cool. That looks good. And then instead of doing it this way, let's take this same time 1 and put that through a ramp, right? And this is how you can think of kind of writing your own Vex without having someone to kind of walk you through it, right? You can take that time 1 and be like, oh, I just want to refit that. That's going from 0 to 1 already. So any like function that goes between 0 and 1, I can use that to kind of drive it, like a ramp, for example. So here we're going to do a ramp called blend ramp, and we can then we'll use the time modulo 1 as the x-axis for that. In fact, this doesn't go there. My bad. This goes at the end here. Just going to tidy this up a little here, like so. Great. And that should give us what we need. And I'm going to hit this just to kind of create our ramp parameter here. So now this is going to be looking up, so this will look up from 0 to 1. And it's going to do the exact same thing because we're basically setting 0 to 0 and 1 to 1. So what we can do now instead is take this, put this in the middle. Now it'll go halfway and kind of stop and then snap. And then we can add another point here and it'll go halfway and go back, right? So now it's going to go back and forth. And if we wanted to, we could shift click all of these, select them all, go down and do something like monotone. Oop, that's weird. That should have. Oh yeah, it did. We're just not seeing it update. You could also do catmul rom. And this is where that set this live parameter display. If we had this on, we would see that. So as we change this, you'll actually see how that is changing, right? So that's kind of a weird one too. It's like boom, boom. Kind of got this interesting little bounce going on to it. However, the problem here is that if I click on, let's say this one and try to drag it, it's going to keep them all selected. It won't let me just unselect that one. So if I click live parameter display, click, oh, no, they're all selected again. There's definitely a difference there. I can't think of where that situation is, but there's sometimes where that works and sometimes where it doesn't. So anyways. Yeah, that's fine. Anyways, let's keep going through. I'm not going to figure out why this ramp was acting funny. All right. So we have that all working. Let's instead now play around with this a little bit more. So we're going to have 2 quaternions that we're going to use. So this, instead of doing the version, the situation that we did before, instead of just, popping between those, kind of flipping back and forth between those different directions, now this is going to actually interpolate between them, right? So the one that we did way back up here, where it was kind of randomly kind of going around, we're going to do that same thing, except give it the ability to kind of smoothly rotate. So that's what we're about to do here. So, yeah, we can keep some of this stuff and we'll kind of see what we can use from here. So, let's declare some variables here. So we're gonna have a couple vector 4s. Sorry, it looks like, nope. Okay. Seems like everything's okay. Got a little, funky message here. Let me see if this, sorry, I'm getting a little weird message from my, stream. Give me 1 second here. Just going to make sure that everything is running okay. Seems like we're good. Great. Well, I'm guessing this is just a little error on my end. Not on my end, I shouldn't say, but on my streamer, my streaming platforms. And hopefully it's nothing that's causing any issues. If you guys are seeing any issues in chat, let me know, please. But I'm going to keep rolling along because I think everything's fine. I think everything's fine. Don't think we've got any issues here. All right, I'll leave that up and just keep going. All right, cool. All right, so with vector 4, we're going to use the target. We're going to make a target and a base. We're going to do a vector for the axis. We're going to do 2 floats. Don't need to do it plural. Seed and blend, just like so. All right, let's get rid of, I don't know if we'll need to get rid of those or not. Let's just keep going here, and I can always grab from those if I need to. All right, so we're doing axis equals CHV axis. Some of this was from before. I'm just going to kind of go through as quick as I can. Let's delete our spare parameters. We'll remake those in a second. All right, here we're going to normalize our axis just like we did before to make sure that the axis is just a direction and doesn't have any magnitude, beyond just 1 unit vector. So let's do normalize here, and we'll normalize the axis. All right, we're going to work with the seed float next. Our seed value is going to be first set to the noise of the position plus time. So that's going to be our kind of random noise that we've got there. We're going to use that for our seed. And then our seed is going to get run through a ramp that we're going to call noise rerange. And we're going to put seed as the x-axis of that ramp. Cool. And then next we're going to say axis. We're going to multiply that by the truncated value of seed, which is the noise and the ramp, you know, the refitting of that seed value. We're going to do that seed times 4. So that will be, you know, setting that 0 to 1 range, right? All that kind of stuff. So we'll do seed times 4. And then we are going to multiply that times pi divided by 2, which is going to be a 90-degree rotation. Cool. All right. Good. So now we're going to have our target quaternion set equal to the quaternion of the axis. And if you remember, we're taking that axis and multiplying it basically. So here we're taking axis and we're scaling it by this, right? So that's the random kind of noised and fit with the ramp. So we're doing all of that and then multiplying the axis by that. So again, when you remember, you take just a vector and you scale it, that's going to rotate a quaternion. So that will give us that kind of random target that we want to move to. And then we're going to have our base, which is going to be just the set equal to 0, 0, 0, 1. So that's that just default kind of orientation. And then finally, we're going to set blend. And blend is going to be using a different name here. We can call it anim. And it's also going to be time modulo 1. So it's going to be using that modulated, you know, the modulo time where it's kind of going to 1 and then back to 0. And then down here, we're just going to change our slurp between base and target instead of A and B. Okay, looks like we've got some stuff happening here. Let's initialize all these kind of parameters. Our axis, let's do it in the 0, 1, 0 axis again. Let's hit play here. Sure enough, we're going to have some kind of weird stuff going on, but we can see down here sort of how Matt has this set up. So let's set up our ramps to kind of match that. So maybe we can play this and do it at the same time. So we're going to drag this in, drag this over. So these will be kind of in the middle here. And I'm going to bring this up a little bit, it looks like, and bring this one down. Just going to kind of match this up to it, right? Something like that. We're going to pull this in, and we're going to add a couple more points in here. So it kind of depends on how we play around with some of these values here. But you can see this is more or less what's happening with Matt's as well. So as you play around with these values, you could kind of slide this over. You know, something like that. We could bring these closer together. Maybe bring this up. And there we go. We're kind of using this to kind of filter just through a little section of these boxes, right? So lots of different things that you could do with this, but obviously you can see how we can kind of play around with these different options for kind of transforming these quaternions. Cool. All right. So in one of the earlier options, or one of the early examples, we had the transform here before the point wrangle, right? So if we rotated our grid here, let's just hit play. And we take our grid. Now we're going to see the kind of outline of this. There's ways to turn that off, but I'm just going to leave it for right now. So if we rotate this, it's going to keep the orientation the way it was before as we kind of rotate it around here, right? These boxes stay oriented the way they were. But what happens? Let's see here. Yep, our parameters aren't updating because there. Now they will. Now we'll see them. When you have this off, these don't update. So that looks a little funky. Anyways, all right, so let's swap the order around and see what happens. So if we take, actually what I'm going to do is I'm just going to give that a little shake, drop it down here. All right, so now let's take a look at what happens here. Now we're actually rotating the orientations. So why is this happening? And what can we do to kind of make this happen or not make this happen, depending on where we might have a transform in our network, right? What we can do is we can use this little attributes field here. And it has a star in there, which basically means that anything that Houdini deems as a transformable property will be transformed, right? So things like, normals are going to get transformed as you rotate them, right? Because if you didn't, it would get all funky and not work, right? It would get really weird, and our shading would get all off and look crazy. So instead of that, we want them to be able to rotate as we rotate our object around. Things like color, maybe you wouldn't want to, right? So in this case, it knows kind of what are appropriate attributes to rotate and which aren't. But what we can do is we can say, instead of this, we can say not orient like this. And now it's not going to affect the orientation. So if we do this, now it's going to be the same as it was before, except we have this transformation coming after the point wrangle. So it's pretty, it's something just to keep in mind. It's not going to always come into effect for you, but it's definitely something to know. There's ways to make sure that these transforms aren't going to either are or aren't going to affect your orientation of your, copied objects. So just something to keep in mind. I'm going to set this back, and that will work the way it was before. Same thing. This is also talking about color. Matt gives a little situation here where someone had he'd accidentally pushed his colors to the normals and had some transformation stops in there, and then when he brought the color back from the normals, they were getting rotated, the colors were getting rotated, and so it made this crazy whole mess of color and issue and stuff like that. So that's actually something that can happen, so you got to just be careful of what things you want to rotate and what things you don't. And the way that Houdini knows what these things are is by their type. So if we middle click here, we can actually see that these have, types to them, right? So in this case, we have, a 4 float and it's a quaternion. This is a 4 float and it's a position, or a 3 float and it's a position. There's going to be other things that come in there like color and things like that. So just things to keep in mind, that there's different attribute types even within, just a vector or, what quaternion or matrices and all that different stuff. So something to keep in mind. All right, great. So let's kind of keep going here, and we're getting kind of close to the end of day 17. Hopefully you're hanging in there with me. And hopefully this is all clear enough? If not, please drop questions in the chat. I'd love to hear from you guys. I know it's a Friday night. Maybe everybody's just kind of partying and has me on in the background, maybe for entertainment. I don't know, but hopefully that's not the case. That'd be a little strange, weird party. But yeah, if you guys have any questions, I'd love to, be able to kind of talk through them, or at least give my best explanation of what's going on. So. All right. So the next thing that we are going to talk about is this function called qmultiply. So for now, we are going to be done with our box. So I'm just going to shake that off there. Let's grab this sphere. I already have this set up, but uniform scale 5, frequency 2. This is going to go in place of our grid. So we're going to do this. And we don't need our transform anymore because that's going to make things weird. So let's not do that. Pass this in here. I'm going to set this back to default. So control middle click and delete our spare parameters there. Now we just have a sphere with pretty much nothing going on. And I'm going to get our pig head, put that in here. All right. So we got pigs copied to a sphere. Things are happening. Okay. So let's look at where we're going next with this. All right. So let's set our what kind of Matt just talks through really quickly in text is we could say at n is equal to I can type normalize at p like that, and then at up like so. Oh, I forgot to. There we go. I'm not sure if that changed it at all. Did it? A little bit. It helps. Basically what it's doing is making sure that kind of the bases of these pigs are all facing down, or as close to down as they could possibly go. So it's just kind of orienting them a little bit, right? So their snouts are all sticking out because those are in the z-axis, and we've set our n to be the normal of p, which is going to be all, pointing outwards. So great. That's all working the way we want it to, right? So let's just assume we don't want this, though. Instead, what we would want is the top of their heads pointing out, away from the sphere, instead of kind of with their backs, the back of their head to the sphere. So you could pre-rotate the pig with a transform sop, right? So we could come in here and do a transform, right? We could do this, and what would it be? Like this, right? We could rotate it here, right? And yeah, that's what we'd want, right? So that's all well and good. But what if you then want to have the pigs turn their heads, right and left like this, right? Okay, we could do some animation there, sure. But what if you then wanted to do something where you've got kind of like this random head wiggle in the midst of all of that too, right? That's going to get really, really complicated. There's going to be a lot of stuff going on there. So you could get in a whole bunch of crazy things going on there. Also, with a copy to points, you can't have really individual attributes for each of those. So you can't really have offsets and all that kind of stuff. So there's a lot of frustrating things that'll kind of happen there. So instead of doing that, where you have to try to figure out a bunch of transforms with like having stamp parameters coming back, the old copy stamp idea of taking data from this copy and pushing it back up into these nodes here. We can do stuff with our quaternions and be able to shift them and move them in ways based on the input geometry, and kind of layer transformations on in a meaningful way. So let's keep going here, and you'll see kind of how we can take multiple quaternions and kind of add them together, basically combine them together. So let's first start with this function here. So we got normalize, that's great. So let's turn these into a quaternion, right? So if you remember, what we had to do is do the make transform of those to get a 3x3 matrix, and then do the quaternion function to turn that into an Orient. So here we have Orient, and we need to use quaternion. And then inside of that, we need to do a make transform, and that we can feed our at n and at up, just like so. And what did I miss there? I missed a, let's see what it says. I can tell what I missed. Unexpected semicolon. I was expecting a bracket, so I missed a close bracket. There we go. Control enter. There we go. All the same. Nothing too interesting here. So let's now take another, let's set up another quaternion here. So let's do a vector 4, and we'll set this extra, call this extra rotation, extra rot, equals quaternion. And we'll do this pi divided by 2. That is going to be the angle. And then the axis will be 1, 0, 0. So this is going to be a 90-degree rotation around the x-axis, right? So this is going to do that same transform that we were kind of playing around with here, right? Where we rotated it 90 degrees in the x, right? So when we did this, 90 degrees, it's going to be the same thing. However, this is now going to allow us to blend those together, right? Actually have those go together. So now let's take the Orient and set it to at Orient equals Q multiply. And we're going to take our 2 vector 4s. So we'll say at Orient and extra rotation, like that. So now we have all of these heads kind of sticking out. They've all been rotated 90 degrees, and they did exactly what we wanted it to. So instead of doing this, what's up, Nick? Hi, how's it going? I have no idea how many other people are even here, so hope you're doing well, buddy. My chat freaked out, and yeah. Hey, there we go. My chat is back. Cool. Now I can actually see what's happening here. Anyways. All right, so we've got these. Oh, hi Matt. How's it going? No, don't worry. You don't have to apologize. It's, well, I guess is it Saturday for you? It is, right? A year on Saturday. It must be. Is that right? You have to remind me, because I'm going to New Zealand soon, and I've been thinking about the difference there, and it's like 6 hours behind plus a day. So yeah, you must be like 8 hours behind plus a day. Anyways. International dateline messes with my head sometimes. Anyways. All right. So let's now, instead of setting this just kind of from, building a quaternion that has a 90-degree angle in already, let's actually set an angle slider that'll allow us to kind of adjust that as we go. So we're going to take this vector 4 right here, and instead of having this pi 2, we're going to set this to radians of the, and set an angle here. This is a little compressed for me, so I'm trying to make sure I'm writing this properly. Yep, that looks right. And that's going to be set to 0 now until we get our slider here. And now as we do this, we can see how we can make that rotation, right? So now we can do that 90-degree rotation that we were trying to do before. But we actually have a slider for that, right? We actually have a parameter that we can adjust. So we have our extra rotation, but we could also add in a little head shake, like an animated head shake. So let's do that. So we have our extra rotation. Let's clean this up a little bit here. So we're going to tidy up our code and kind of make this all work the way we want it to. So here we're going to say vector 4, n, and up. I'm sorry, just vector. I read that wrong, which makes sense. Those would be vectors. Vector 4 is going to be extra rotation and head shake, just like that. And we can change these. We don't have to set our normal or our up. We can just set those as variables. We have our orient set there, which is make transform. And instead of it being attributes, we'll just do n and up. Our extra rotation, we don't have to declare that here, so that's a little cleaner. So we have a quaternion, radians, and we can just say, instead of angle, we could just keep this at 90. And then we can do our head shake equals to quaternion of radians 20, so 20 degrees. And that is going to be multiplied by the sine of time, not all caps. Yep, and then times 3, so that's going to speed up time a little bit. And this is then going to be in the up axis to the original pig, right? So this is going to be kind of a vector pointing straight up from his head, goes rotate it back and forth, right? So we're going to do 0, 1, 0, like so. This is getting a little long, so sorry, it's going to be a little hard to read here. I guess I could slide this over just so we've got plenty of room here. Head shake, why is this angry at me? Because I'm missing a bracket, that's why. Cool. All right, so we still just have this. It's not doing anything yet because we need to add in one more Q multiply here. So what we're going to add in here is another orient equals Q multiply. We can use the orient again, right? Because we're just applying these together, right? So we can keep using the same attribute and bringing that into our function a line down. So let's do head shake here. And that should work. So now let's hit play. And there we go. There's our shaken pig heads. So I think we're getting somewhere. Hopefully you're following along. It's all making sense. But now we can just keep using the same idea and get some really interesting results here. So now that was all stuff that we maybe could do, right? Because they're all, they're all equal, right? They're all doing the same thing. But let's add in a wobble onto these, right? So let's do that. We'll do a wobble. And we'll say, oh, you know what I didn't do? I didn't declare that. So I'm going to come up here, declare wobble, and then come down here, quaternion. And in this case, we are going to use the vector version of quaternion. So we're going to set a vector, which is 0, 0, 1. So this is going to be around the z-axis. I'm going to multiply this by curl noise. And that's going to be the position plus time times 0.2. Like so. And then we can actually take this same thing here. We can actually copy and paste this because it's going to be the same thing. Instead of head shake, we're going to do wobble. And now when we play this, we're going to get this kind of random wobbly thing going on here with all these pigs. So that is working in an interesting way, right? And because it's based on the position, those are all going to have their own kind of random wobble to them. But let's just say we wanted to change this a little bit. Let me just go back here and show even one more thing that I think might be an interesting option as well. What if instead of time here, what if we did time plus, maybe this would work. I don't know if this would work or not. I think this will. Let's see. Time plus PT num. So that should give us all, all different shaking, right? So this is something that would be pretty hard to do with just your standard copy to points and doing a transform over here. This really isn't something you'd be able to do because you can't really do that offset very well like that. There are some ways to get around that, but they're not really a clean way of doing it. And in fact, they would probably be a lot slower and wouldn't be this performative, right? You can see we're getting, it's hard maybe to see, but we're getting about 70 some frames at its maximum. Obviously we can lock that to 24, but yeah. So we're getting really good playback speeds. So anyways, this shows some of the, all the different kind of levels that we can take these orientations and kind of build them together and create some really interesting effects. All right. So quaternions are really cool. They're kind of a black box, but they're our kind of Swiss Army knife of black box of rotation, right? So we can do a whole lot with them. And as Matt says here, there's no need to melt your brain trying to understand four-dimensional rotations. So yeah, good. We don't need to worry about that. So what if, though, we need to bring our quaternion back from this four-dimensional world into something maybe we could look at a little bit better, like a matrix? Well, there is a function for that, and we can use qconvert. So I am going to add this back in here just so we've got a nice complicated situation here with all of our pigs moving all over the place, right? And now, oops, if we go down here, we can say matrix M is equal to qconvert at Orient. Now this is just declaring a variable M and setting it to that, right? So what if we wanted to see this in some, more interesting kind of situation, right? We can do a couple things. Let's first just see those numbers, right? Let's at least do that. So let's do, we'll write that to an attribute just so we can at least see that there's numbers in there, right? So let's do, we'll just do at A again, just so it's it's right at the beginning of our geometry spreadsheet here. And we're going to say, I think this is a matrix 3. So I think we need 3 at A equals, and then we'll do that equal to M. That should work. Yep, there we go. And now we've got kind of this attribute that's a, 3x3 matrix, and I can actually click on this and inspect it, and we can just look at it this way. So there's all of our, we've got 1, 2, 3, 4, 5, 6, 7, 8, 9. Got 9. Wait, why is this not happy with me? Oh, sorry. It's supposed to be a 4? Is that what it's supposed to be? There we go. It's actually supposed to be a matrix 4. Yeah. Thank you. I realized that right as I'm doing it. Yep. It's like, why is it yelling at me? Okay. So it really should be a matrix 4, not a matrix 3. My bad. So anyways, this is a 4x4 matrix. We can see that those numbers come through. Either way, it's a matrix. We're going to talk more about those in the next chapter, in the next day's lesson. But what if we want to see that in something, these are all just random numbers. We can't really read those as humans, or, maybe most humans can't. I'm sure, again, someone out there could. Qconvert Orient. I see. Yes. You could do matrix 3M here, do 3AM, and it's not going to be angry at me because I'm declaring a matrix 3 and it knows. Yeah, great. Thank you, Matt. That makes perfect sense. So yes, you could declare matrix 3M and get it that way and write it out as a matrix 3. Or if you just say matrix M, that's going to be a 4x4 matrix. And those are just 4, 3. I don't know if there's a 2x2 matrix, but anyways, yes. So now we can see something's happening, but let's make this more readable for, human beings. And we'll do a couple of vectors that we can look at here. So I already have n and up set in here. So we're just going to take a look at those here. And I'm going to go back to these, this point wrangle here. And so you can see right here, we've got our normals, but we're not writing anything out here. We're not declaring anything. So they're just pointing kind of in our standard normal direction. So now what we're going to do is we've got this matrix. Instead of just doing it as a matrix 4, we're going to change this to a matrix 3, just like Matt talked about a second ago there. So this will give us a 3x3 matrix, which will just give us our scale and rotation, not the transform of it. So this is kind of the smaller, less involved matrix. And we can then get a normal vector and an up vector from those. So now what we can do is we can say at n equals, and then we're just going to set this vector 0, 0, 1, and then multiply that times m, because when you multiply that's the wrong one, sorry, like that. When you multiply a vector by a matrix, it's actually going to multiply it by that kind of transformation that's baked into that matrix. So that's kind of a nice little thing to keep in mind, right? So, okay, so we've got our normals, and yeah, already we're getting something. They're kind of moving around there. So that's cool. Then let's do our at up equals, and this is going to be in the y-axis, right? So we're going to do 0, 1, 0, and we're going to multiply that times m as well. And there are our, now I've colored these already. I've gone in here and colored these, but if you want to right click on these, sorry, I'm going to start back here. We'll go to I, and we can click on N and click on up, and that'll add those vectors into our like visualizer, right? And so if we look at this little icon here and right click on it, we can see that these two are being visualized in our scene. However, they're both yellow by default. So you can just go in here and edit them. I changed the N to blue since that's displaying our Z axis. And then I can come up here and go to up, and I change that to green. So that's why they're blue and green, so you can see them a little bit better there. I'm also going to do extract all points. And that way we can just see our points here, and we don't have to worry about that whole, geometry in our way. Let's hit play, and we'll see there's our two axes kind of wobbling around on us there. The blue one's probably a little hard to see, but I promise it's working. So then another thing that Henry actually had given Matt the idea of was that you could just extract the components of the matrix directly, which makes sense because we're basically just taking just this straight up straight in the z-axis and straight up in the y-axis and multiplying them by that rotation. So if we just pull out the those axes from those 9 values, each of those there's 3 values that are one vector, 3 values that are another vector, and 3 values that are a third vector. So we can just take out the one vector, and that's going to be our y-axis, and the 2 vector is going to be our z-axis. So let's do that here. So what we can do here instead is we're still getting the matrix 3 from the qconvert of the Orient. We are going to create a vector axis like this, right? What we're going to do is set that equal to m. And then what we can do here is we can say at n equals normalize. And then we're going to take the axes and get the second one for the z-axis, which again, if you remember, the second is actually the third because we start at 0. So that's going to be our z-axis, and at up equals normalize axis 1. And I think, sure enough, that does the exact same thing. Nothing changes. Everything works. So that means we're good. So there we go. We have reached the end of day 17. I'm really glad I didn't do this last night at 11 p.m. Because my brain would have melted. So there we are. Lots of orientation stuff, lots of matrix. The beginning talks of matrix. The dark magic of quaternions, and yeah, a lot of fun things in between. So if anything in this was not making sense to you and you want to talk about it in the chat, please feel free to throw a question in there, comment. You can heckle from the back of the room, whatever you might want to do. Totally fine. I'm here for all of it. And yeah, so why don't we talk through the exercises? And if you guys have any questions, then we can read those and kind of jump back. Thanks, Nick. I'm glad you're very confused. To be fair, Nick is not a Houdini user. He's just here to make me feel better. So I'm not talking to a completely just Matt and no one. But yeah, Nick is very confused. So my apologies that, sorry, Nick. We'll talk about it later. I'll sit you down and give you a little lesson on, linear algebra and stuff. Anyways, all right, let's talk about these exercises. So one of the exercises is copy a bunch of eyeballs to a grid and make them all look at a single point. So if you remember, we had done some stuff before where we had all of the points on a circle, maybe looking at one specific point in space, connecting to one point in space. Maybe think about some of the concepts that are involved there, and that will help drive your thought process on how to make all those eyes look at one point, right? Extend the above to give the eyeball, I don't know what that word is, saccades? Not sure what that means. Little random rotations to make them more lifelike. So maybe give them a little wiggle. So if you think about it, we've added some wiggle to those pig heads. So how would you add some maybe wiggle to the eyes? And then extend that even further so that you can have a slider so that they all look in random directions when the slider is at 0, but then focus on the point when the slider is at 1. So that is, those are the exercises for day 17. There's a little bonus at the bottom here, but to be completely honest, I didn't read through it and I have no idea what it says. And I'm just going to be honest. I forgot to read through that. And yeah, so we could read it real quick. But you can read it on your own too, because I don't need to sit here and read stuff to you, I guess. But it's talking about the set attrib type info command, and basically I think that'll set your types of vectors. There's a link there to the docs from on the side effects website, so you can go there and take a look at how that command works and what you can do with it. So cool. All right, looks like we don't have any questions, which seems wrong, but I can't make you ask me questions, so we're going to move on to day 18, and we're going to start talking about intrinsics. All right, so we are going to start. Let's kind of get our scene back to a little bit cleaner setup here. I'm gonna get rid of that. We don't need that anymore. We're just gonna use a sphere and a transform. We can get. We'll probably be tweaking that in a second, but there's a sphere and a transform here. Great. Oh no, that's the extract points. We don't need that. And I don't think we're going to be using this either. I'm just going to keep the pig head around just in case we need it. All right, let's clean it up a little like so. Do a transform. And we're just going to copy the values that Matt had given us here. Let's just set this back. Actually, you know what? I'm just going to name this JOV day 17. And this will be 18. And let's set this, delete the spare parameters, and we're back in business. Lovely. I think we're going to use this shortly, but what we're mainly going to be looking at is this sphere, which we're going to set to the primitive mode, which just makes a sphere, gives us 1 point, 1 primitive, right? You can see here, 1 point, 1 primitive. And we're going to transform it to make it do something maybe a little bit more interesting. So let's use these values here for our scale. So we're going to do translate 0.8, 0.6, 0. Rotate's going to be 45. What the heck is going on here? 10. I must have done something weird here. 58. I don't know what I did. I must have hit a button weird. And then the scale 0.7, like this. Okay. So we've got this kind of hamburgery looking thing, weird sphere thing. Okay. So we've got this, right? But where is this information getting stored, right? We have a point here. There's some information there that's been changed. We've got a primitive here. Like, where is this information being stored? So you might think, okay, it's being stored in this transform, SOP. That's sort of true. Yeah, the SOP is making that happen. But, we could write this out to disk, bring it back in. There would be no transform SOP, and it would still have this transformation. So where is it being stored, right? Like where in this geometry that's being stored to disk are we actually getting these transformations, right? And the answer is a thing called intrinsics. So, the translate we see here, but there's got to be some rotation. There's no orient. There's nothing going on there. So what we're going to do is we're going to look at this thing called intrinsics. So let's go to our primitives here. And if you notice, when I click over there, we get this little intrinsics drop down here that pops up. And if we click on it and say show all intrinsics, whoa, now we've got some attributes in there. And there's a whole bunch of stuff going on here, right? A whole bunch of data that we could work with. And so we could select them all, or we could say hide all intrinsics and just grab some of them, like maybe transform and measured area, right? So the dictionary definition of an intrinsic is being an extremely important and basic characteristic of a person or thing. So these are important characteristics of the primitives, basically. So in the intrinsics, there's a spot called type name. In this case, it is a sphere. There's other ones that can be done like a tube, metaball, circle, poly, sphere, and packed geometry. So when you have your packed geometry that's being represented by just a point, as those are being transformed, like say from rigid bodies or something like that, those transforms are being stored in there, but they're not always specifically maybe being written by an attribute. I think coming out of RBD, they actually would have an Orient attribute, but you could actually describe them through their primitive intrinsics, right? How they're rotated and all that kind of stuff. So, so one of these that we'll find in here is a 3x3 matrix called transform, right? And the interesting thing about transform is if you look at it, the rest of them are these kind of grayed out colors, but this one is white. And we'll see that that has a reason shortly that we'll be able to actually manipulate that. So, okay, so a 3x3 matrix, we talked about that before, what it is, kind of what it does, right? So if we wanted to set the identity matrix, that would be defined as this 3x3 grid of numbers right here. And you can see that the first one's set only to 1 in the x-axis, the second one is 1 in the y, the third is 1 in the z. So that creates our identity matrix, right? So if we were in Vex, for example, this matrix 3 of M, maxtrix, mistype. If we set it equal to this, it would be 1, 0, 0, 0, 1, 0, 1, 0, 0, 0, 1, like that. That would be how we would write it. And that's obnoxious, right? So there is a quicker way to write this. And again, just remember this is the no rotation, no scaling matrix, right? Just like we've done with some of these previous ones like Orient and things like that. When we wrote Orient as 0, 0, 0, 1, this is the same thing. This is just everything is in its kind of world transform. And so instead of writing it with this convoluted series of zeros and ones, what we could do is just use the identity function. The ident, like this. We don't have to give any arguments, and that's going to be exactly the same. It's going to set it to the same exact thing, right? So just like I was mentioning before, these are gray, these are white. Basically, the transform one we're able to actually write to. It is read and write. The other ones are just read attributes. We can't actually manipulate them. So if we look at, we'll just say show all intrinsics, and we slide down here, there's really nothing else we can write except for this transformation right now, right? But if we use that transform and we use this position, we could set that back to what, this sphere was when it was first created before the transform was put in. So let's look at how we can do that. We need a function to be able to get in there and tweak those. We can't just write those as attributes. They don't just automatically write themselves. You need to use a function in order to write to an intrinsic. So we have this identity. So let's now set our primitive intrinsic with set prim intrinsic right there. So we're going to do set prim intrinsic 0. So we're going to do it on the first geometry. We're going to set it to there we go. Transform. And we're going to set that to, so the ID, the prim ID we want to write to, and then the value. The value is going to be the M. So we're saying what geo input to use, what the name of the intrinsic is, what prim number, there's only one, so that's all we're going to do, and then what's the value that we're writing. We'll give a little semicolon at the end here, hit enter, and sure enough, we are back to square one. The only thing that isn't on is the position. So if we were to set, in this case, I'll just kind of get to that next logical step. If we just did P equal to 0, 0, 0, just like this, obviously that would set us right back to where we were at the start. So this here and this are actually different. And I think the reason is because the scale, I think, yes, because I had a uniform scale here of 5. So here we're going to do a uniform scale of 1, and now they're back. That was the difference, was my scale. There we go. So those are exactly the same. This transform is going to kind of move it off to the side, and we can actually put it right back using this. Now, obviously, we need to set the P, or else it's slightly off from the origin, but a very easy thing to fix. All right. So what happens if we apply scale and orient to our sphere, right? Well, the answer is nothing, right? Orient and scale really only have an effect when you feed it into a copy stop, because those are things that are looking for those instance attributes in order to scale and orient things. But what if you had those attributes and you wanted to drive something like a primitive, that has an intrinsic on it, right? Like a sphere or whatever, something that's, packed geometry or whatever. So what you would have to do is go in and actually update that prim intrinsic yourself. So what we can do is we'll take those orient and scale attributes and then do some multiplication to be able to set our matrix to those values, and then set those values to our prim intrinsic. So all right, let's do that now. So let's take out this transform here and we can see what's happening. So here we're going to first, we can just leave this set prim intrinsic, so we're going to do that at the end anyways. All right, so let's do at orient, and we're going to make a quaternion here. This will be the vector version of it. So we're going to do 0, 1, 0. And we're going to multiply that. Multiply that by time. Like so. Then we're going to set scale. And just remember that this orient doesn't need the descriptor in front of it because it's a known attribute that we're looking for here. Scale is not one of those that's kind of defined that well. So 1 comma 1.0. Oh, sorry. I'm reading this wrong. 1, and then we can do 0.5, and then comma 1.5. Like that. That's going to be our scale vector. Now what we're going to do is we're going to make a matrix 3x3 matrix called M. We're going to declare that and set it to the identity. From there, we're going to scale it. So we're going to scale M by the vector scale. In fact, I think what we want to do is do V at scale, just to be a little bit more clear. Should actually be able to figure it out, but let's just be more straightforward with that there. Then we'll do M and do times equals. So we're going to multiply this by qconvert. So we're going to be taking that orient and turning it into a 3x3 matrix, I believe in this case, and multiplying M by it. And then set prim intrinsic is going to be 0 transform. Yep, because we're changing the transform. And we're just going to make sure that it does it by at pt num. Doesn't really matter here because we have just 1 in this case, but we can do it that way. Unless I missed something that Matt mentioned that we should do. But I guess if you had more than 1 point, we could do it that way. But what this is going to do is going to kind of give us this squished, weird orientation here. We could up the scale in an axis, like one of the axes like that. We could and this is actually going to rotate around like so. So there we go. Now we're taking this primitive and updating it using these orient and scale. So that is pretty much doing exactly what we'd want it to. One of the things you might notice in this little code block is that the scale isn't set to anything, right? It's one of those special functions where it does an in place, function, and you don't have to assign it to a variable like you normally do. So if you did something like this where you did M equals scale M at scale, that's going to error. It doesn't need to do that. So the reason for it is like there's a couple other functions as well that do this same thing, and you can actually have them return multiple values from one function. So like you can't do this sort of a thing here where you do prim ID distance and UV equals to this. That doesn't make any sense. So instead what you'd have to do is do this XYZ distance and then have your prim ID distance and UV. These are all actually going to get returned from this function. So like it's going to maybe calculate based on these things and then return these values so you can use them elsewhere in your code, right? So so this sort of makes sense in this case with scale, but the one, this is kind of a weird corner of Vex that maybe doesn't make that much sense because it's really just returning a single matrix. So why do you need to do this? Scale and rotate both do this. So it's just something to keep in mind that scale and rotate are two of those functions that work like that. Great. So we've kind of worked through this code, right, and made sense of it. But what we can do, so basically what Matt's saying is the main thing to keep in mind here is you construct a matrix out of instance attributes, apply them to, and then apply them to transform intrinsic as if you were using a copy swap, right? So we're kind of doing what you would in a copy swap, but we're basically just going through all the points and taking the orient and scale basically and applying those to the point. So if the attribute orient and scale existed, we could actually just pull them in and apply those right to each of these transforms. So cool. That's working just fine. So the transform intrinsic is a matrix 3, right? That's what we've been talking about. What we have, if we had packed geometry, would be a thing called packed full transform. And that's a 4x4 matrix. So let's take a look at this here. So let's actually get some packed geometry. So instead of doing a primitive, we'll just do a polygon like we have before and just pack it, right? So we'll pack this. Now we have packed geometry, right? And if we look here, we should see, where is it? In our list of intrinsics, right? That's why, because we're not actually seeing it. So if we do show, we'll see all of our intrinsics. And if we look here, we have a packed full transform. And this is actually going to be a 4x4 matrix. So one way that we can actually convert from a 4x4 matrix to a 3x3 matrix is by basically just casting like this, just like we've done with other values in the past where we maybe have cast them to float. This is another way that we can cast an attribute from a matrix 4 to a matrix 3, right? So what we can do is, if we wanted the full version, we can actually get that and store it in just a variable, and we'll call that PFT. So let's do that here. So we're gonna go back to our points so we can just see that. And we don't need to really have any of this stuff right now. Let's just, I think we can just clear that out. I think we're good. So let's just clear that out. And what we're going to do is we're just going to say matrix. So this is going to be a 4x4 matrix. That we're declaring. We're calling it PFT. And we're going to do prim intrinsic like this. And this is going to read a prim intrinsic, right? So first we're going to give it the geometry. Then we're going to give it the name. Oops. We're going to give it the name of the intrinsic. So this is going to be packed full transform like that. And then we're going to look at the point number like so. Cool. Let's just hit enter. Everything looks good. It's all evaluating. That's great. So if we wanted to debug this and actually see, what this is actually doing, what we can do is say this is a 4x4 matrix, call it A, and just write PFT into it. PFT for packed full transform, and hit enter there. And now we can see, sure enough, if we inspect this, we have a 4x4 matrix, just like so. And if we threw this transform in there, for example, now we actually are not seeing that value. Oh, actually, I'll put this after the fact here because that's not actually transforming it. It's packing afterwards. So now if we look at this, it's going to have all different values in here. But what we can see, a couple things are kind of obvious here that we can see between these two. We have this last column that is going to remain the same. So we can kind of use that as an indicator, right? Because here's what our 4x4 matrix looks like. Here it is all in a line. Obviously, these are both kind of hard to read, right? But let's kind of take it one little chunk at a time, right? So at first, we're going to have this first line. It's going to end in a 0, right? Each of these lines are going to end in 0. The last one's going to end in a 1. So here's our first 4, right? We see that this ends in a 0. The second 4 are going to end in a 0. There we go. The third 4 is going to end in another 0. And then the fourth set here is going to end in a 1. So when we're looking at this matrix, what we can see here is this green section is going to give us that 3x3 matrix, right? And that's going to be the rotation and scale. And then the red section at the bottom is going to be our transformation. And that we can actually read really easily. Just it's very human readable because we actually put those values in, right? These other ones, we'd have to think about how to change these rotations to, orientation into 3x3 matrix and all that kind of stuff. But with the translate, we can see this plain as day. 8, 0.8 right there, 0.6 right there, and 0 right there. So those values have now been written into this transformation section of our 4x4 matrix. So what we could do is just pull out our rotation and scale by we could see that in and of itself. So let's do that. So what we can do here is say, we can make a matrix 3, call that rotation and scale like that. We'll say matrix 3 of PFT. That kind of rhymes. Then what we will do is we'll make a attribute called B, 3x3 attribute called B, set that equal to rot and scale, just like this. If we hit enter, now we've got that attribute there as well. Can we inspect both of these at the same time? I'm not sure if we can. I really hope we can. Yes, good. Okay, so if we slide this all the way over like this, I'm just right clicking on those, by the way, if you couldn't see what I was doing there. And let's look at this, right? So we can see now that this has pulled out just those 3x3 values. This is right there. These are right here. And these are right here. So we've now taken our scale and rotation and written it into its own 3x3 matrix, right? So why all of this, right? Well, when you start, I kind of mentioned this a little bit in the last day, but when you start messing around with bullet, packed primitives, copy, SOPs, things like that, there'll be these edge cases where you want to transfer animation from one group of elements to another. Maybe you've got a bunch of points animated in a certain way and you want to have a bunch of spheres or something go in that same direction, or a bunch of some other type of primitive or whatever. There's all these different edge cases, right? These are things that you just need to understand where to find them so that you can at least know where to look to get them, right? Because otherwise, if you would have come across this right here and not known about intrinsics, you'd kind of be lost as to knowing where to find this transformation data in all of this information here, right? There is no rotation and scale that you can just easily grab, right? So if you're doing something like Alembic archives, there's an ABC full transform in there. That's one of the intrinsics. Packed fragments versus packed disk primitives can each be a little bit different as well. Intrinsics are really useful, basically, and you need to kind of know where to find them in order to kind of clean up those edge cases so that you can actually get your data from one place to another. So this does seem a little messy, right? Matt even mentions it here. It seems like this kind of feels all maybe messier than it needs to be. If you want to, put out an RFE to side effects, you certainly can. That's a valid thing to bring up and say, maybe give some suggestions on, it would be great to be able to see intrinsics maybe in a different way or do something like that. Maybe instead of it being a drop down here under primitives, maybe it's like its own little button here that's intrinsics or something. I don't know. There's things that could be suggested to, all the developers at Side Effects that could be helpful to all of us. So putting in RFEs is never a thing that anybody's, gets frustrated about at Side Effects. It's great to hear feedback from everybody and be able to make a better product kind of as we all move forward. So, so there's other intrinsics as well. This was one I was trying to understand myself. And Matt's example here was there's a closed intrinsic that is read-write. You can use that to convert polygons to polyline outlines, which is an interesting thing. And I'm not even totally sure. Oh, maybe if I do this, let me see here. I wonder if I do this, if I use a grid that isn't that way, no, there's no, is there intrinsics there? Ah, that's what it is. That's what it is. Okay. So, okay, I found it. We're in business. I'm going to turn these visualizers off. So let's write this right here and see what it does. Because I actually didn't try this before. I was like trying to figure out what this even meant, but now I got it. All right, so we're gonna give an open close attribute here. We're gonna cast this to an integer, and we're gonna use a random function and use the prim number. Oh, this is gonna need to be in a prim wrangle, I believe. Yeah, I think this needs to be in a prim wrangle. So we'll do this plus at frame. So we'll use the frame number instead of time this time, and we'll multiply it by 2. So we're just going to scale it up by 2. I think that's good. Is that our last semicolon there? Cool. And then we're going to do set prim intrinsic. This does not need a, this is just an in place function. So we're going to do it on the 0, the first geometry. We're going to do the closed attribute because you can see the intrinsic is called closed. We're gonna go over each prim number, and we're going to set this equal to, if I can type, open close. So this is going to be a random integer, right? That's going to go back and forth between 0 and 1. Yeah, it should go between 0 and 1 because the int is actually rounding it. So it should, maybe it'll go to 2 as well. I don't know. But anyways, doesn't matter. Let's just click it. Oh, wow. I just made Houdini real mad at me. Okay. Well, there we are. Sorry, folks. Give me a second here. We'll be back in business in a second. Oh, probably because I was in the point attribute thing. Yeah, that's probably what it was. Let's see if we can recover this. Hopefully it will. Did give me the crash file right away, so let's see. Yes. Okay. There we go. Didn't like that. All right. There we go. That's what it's supposed to do. So this is randomly, what this is randomly doing is assigning these to be open or closed polygons. And if we hit play, they're going to like freak out and go nuts. So yeah, there we go. Or actually, maybe it should be points. I don't know. Nope. Does the same thing either way. Kind of a weird little thing there, but yes, there we are. There's some other intrinsics to talk about. So sorry about the little crash there, but that is the end of day 18. So, if you have any questions, please feel free to put it into the chat now. I'd be happy to, take a look at anything that you guys might be wondering about or anything that we can help clear up before the end of the stream. I will go through the exercises and then we can come back and take a look at the questions if you have any. All right, so the exercises. What other intrinsics can you find? So what you can do is check what's available on some of the more exotic geometry types like volumes, VDBs, or packed alembics. We've also gone through like the most common attribute types and how to define them by prefixes. But you can search the help to find the full list, right? So there's other attribute types that you can be able to define, right? Then what other intrinsics are writable? Look through the intrinsics, see what are writable. Remember the writable ones are the white ones versus the gray ones. And then are there any intrinsics at other geometry levels? Point intrinsics, vertex intrinsics, detail intrinsics. I'm going to say that there are in some cases, but I'm not sure where. But I think there are. So yeah, take a look, search around and find. So that is day 18 of the Joy of Vex. So we are one more stream away, and that stream will be tomorrow in the afternoon. And, tomorrow for me. That will be at 1 p.m. Eastern time. And we'll be finishing up days 19 and 20 and closing out this series. So thank you guys so much for joining me tonight and joining me throughout the whole series. Hopefully it's been a really helpful thing to be able to, see how this all works and just grow your understanding of Vex and kind of follow through the process of kind of learning new functions slowly along the way and new ideas and concepts. Huge thanks to Matt as always. His website is super, super helpful. And if you find yourself using his website really at all, you should just throw him a little thank you through Patreon or through PayPal or whatever. Give him a coffee, whatever you find reasonable to send his way. I'm sure he will appreciate it. But that is the stream for this evening. Thank you guys so much for joining us. And we will be here tomorrow at 1 p.m. Eastern time and be doing the last 2 days. So I will see you, shortly. It's not that far away from me, but I'm going to go to bed, wake up, and we'll do this again. So I'll talk to you guys soon, and thank you for joining us. See you tomorrow.